Now what we are going to talk about before the molar conductivity, I see we have to refer this. Well, there is what we call conductivity of solutions. Now, this conductivity of solutions is based on the fact that conduction of ions within solutions. Take an example. If we have something of this kind, then we have electrolytes. Take an example. This is the first electrolyte. Then this is the second. What we do, placed at a distance apart in a solution. Remember, these are in solutions. They are placed at a distance, say L. Each has cross-section area A. Now, this is for the electrolyte. What do we see here? That the conductivity of solutions or resistance of solutions, first of all, we can say that resistance is inversely proportional to the cross-sectional area, and resistance is directly proportional to the distance placed apart. This is cross-sectional area, and then this is distance between electrolytes, and then this is resistance. Take an example. We say that when the cross-section area, the resistance and the cross-section area, take an example. We say an increase in the cross-sectional area decreases resistance. What do we mean here? Take an example. When the cross-section area is at least 2, then resistance drops maybe to a 0 point. Reason being that wherever we increase the cross-sectional area, we increase the surface available for molecules, or like for electrons to bind and to conduct, meaning that we lower the resistance in that case. But with length, wherever we increase the length between electrons, when length increases between two electrons, less ions will be able to reach electrodes. Thus, conductivity is lowered and resistance of an electrolyte increases. That's why resistance is direct proportional to this, that when we increase this, that ions moving like from this space to reach here and to reach here to conduct decreases. As it decreases, then conduct resistance increases because conduction has decreased. Now, when we combine these two equations, we shall have what we call resistance. We've said it is directly proportional to length, but inversely proportional to cross-sectional area. When we remove the proportionality symbol, we get resistance as equal to out of L out of A. What do we say? This is the proportionality symbol. This is for resistivity. And then this is the cell constant. And then this one becomes the resistance. But when we find the reciprocals on both sides, we shall find that 1 out of R is equal to 1 out of the constant for resistivity, then it will be also A out of L. This will remain the inverse of a cell constant. Then this one now turns to what we call then we shall have also this one forms, this is conductance, this becomes conductance, and this becomes the electrolytic conductivity. This one can be denoted by a G, and this one can be denoted by a K. Now, when you say that, we say, meaning that for the same case, we shall have a 1 over R is equal to 1 out of this A out of L, such that if we denote this by a G and this by a K, we shall have A out of L. But when we want to use this, the electrolytic conductivity, then we shall have a K as a G. Then after finding the inverse here, we shall be A over L over A. Again, this is what we call conductivity. Then we say electrolytic conductivity. This is the conductance of an electrolytic volume, conductance of an electrolyte placed between two electrodes of unity cross sectional area and 1 meter apart, meaning that we write them in form of constants: unity cross section area, unity distance apart. Now what we say, there is conductivity, the increasing conductivity, or like conductivity of electrolytes. We take an example. The moment we have what we call the sodium ions, will be less conductive than the calcium ions and less conductive than aluminium ions. You see that these ones, because this one has less electrons, it donates less electrons, this one more and this one more, meaning conductivity increases with increase in the charge on those atoms. But in aqueous solution, we reverse. In aqueous, aluminium ions will be less conductive than calcium ions, will be less conductive than sodium ions. Just because this one, because it needs more electrons, it binds to more molecules of water in a solution. If it binds to more molecules, meaning that it becomes heavier than all the others, that's why conductivity decreases for larger ions in a solution than for smaller ions. Then we come to what we call the molar conductivity. We say molar conductivity, we say the conductance of an electrolytic volume. Yes, conductance of an electrolytic volume of a solution containing one mole of electrolyte at any dilution. What do we mean? That molar conductivity is equal to the conductance at any dilution. This one we call it electrolytic conductivity, and this one is the concentration at any dilution, and this is the molar conductivity. Now what we say, molar conductivity of an electrolyte, we have what we call the strong and weak electrolytes. Take an example. We have, take a note of this graph. We have this and something of this kind, such that for this one is for the strong electrolyte, then for this is for the weak electrolyte. How do we find this? That molar conductivity it decreases with the increase in concentration. What do we mean here? We say molar conductivity for strong electrolytes decreases with the increase in concentration. What are we trying to mean by this graph? We say that at low concentration, ions are far apart from each other. If they are far apart, interionic attraction is low, and ionic, this which